See, it can be done. See here. There are actually many pretty easy problems in there, right?
Yeah.
Yeah.
More so than the others.
The first one you said sketch. That's
This one is somewhat calculational. So, so as a general point of order, going forward, you guys can skip 3 of the following missions, like problems in each mission and quiz.
Oh,
Not test,
it wouldn't
but
count.
not test. Yeah, you just can skip.
Wait, each mission?
Yeah.
We can skip 3.
I think I've got 15 problems in each mission.
Yeah.
I will grade 12 of them.
This changes the whole game.
Too bad we didn't do that for the past mission.
Wait, so does that mean I can get points back from the
However, if, no, it does not. However, if there are book problems and problems I've written, you may only skip book problems. You're not allowed to skip my problems.
Yes.
So.
Wait,
The book problems are the worst.
so like for this, like Jeff's problem.
They're more annoying.
You
Yeah.
wrote that?
Yeah, well, there are no book problems in this current mission.
Oh, perfect.
So you can skip any 3. Yeah.
Oh, so we could skip any 3 of this.
Yep.
But would you really dishonor Jeff by skipping Jeff's
That's
problem?
what I'm saying. But also then you get to like the issue of
They're more
you skip a
annoying.
problem that's on a test that you have to do eventually anyway.
Well, this is true. While I'm giving you license to skip them, I am not giving you license to ignore them.
Right.
Yeah, that's true.
So.
But I figured this should help you with your time management a bit.
Time management. No, that actually really does. Thank you.
Hmm.
That's so delightful.
I know.
My week just
Let's
got
turn
so
on-
I told you I'm a harmless, lovable fuzzball.
That's like 3 hours now,
me
like
that.
gone.
I've told many people that.
Oh, I have that. I got 3 hours back of my life.
All right. Well, I guess I'll start with a word of prayer.
Yes.
Dear Heavenly Father, we thank you for this day again. I thank you for this class and this opportunity we have to meet and study your creation. Just pray that you would be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen.
The attendance sheet.
I do. And I also have a top hat code, 7538.
You're so intentionally gracious.
I like that. Can you mark me off? I don't have a pen with me. Mark me off.
Some may have
Because I
found
left
a
my
take-home
entire
test to
pencil
be a
pouch
pain,
at my.
but it really was like saving grace.
I tell you what,
No, I haven't.
And you knew that.
I tell you what, I want to believe that. I usually believe that, but there was a semester in linear algebra that I gave a take-home quiz 2, and because of that take-home quiz, I had to talk to Professor Young at the end of the semester because the students complained so severely over it.
Wow.
Over a take-home quiz?
Yes.
I will take a take-home quiz any day over a quiz in class.
Well, you haven't seen the take-home quiz.
No, they must not have had like Sprano for 200 or abstract.
Oh, they did. They did.
Really? Because his 200 take-home quizzes take at least like 48 to 72 hours,
Yeah.
like work time.
Now, in fairness to that class, as I look back at that particular offering of linear algebra, it is, considerably more sophisticated than any other time I ever taught it. So, but anyway, here's the theorem. Let's get to it here. This is, I will call this complex FTC1. And we have D star-shaped domain, f of z holomorphic on D, then f of z has primitive on D, unique up to constant, additive constant. And you can write a formula for it. F of z is equal to the integral from a to z of f of zeta d zeta. All right. Where a is the star center of D, and the integral is taken along some path from a to z. All right. So just to draw a picture of what's going on here. So A. And the point is, if that's the star center, you should be able to reach any point in D by a line segment, right? That's what it means to be star-centered. So like, if I was to foolishly illustrate this, see, every point can be reached by a line segment.
Is that zeta? Or however you say it?
Zeta, yeah.
Okay.
If you don't like that, you can make it whatever letter you like, but sometimes I make that Z, but I'm going to call it zeta today. So the star center. And the point is, well, anyway, this is straight up a formula. Now that this could be any path that goes from A to Z, right? But I prove this in the notes using line segments, and I'm allowed to do that because of the star-shapedness, all right? And something has to give because I had that day of stupidity, so this is one of those proofs that's going to get left out. But the proof is on page 86 of my notes of this. What I think is perhaps more interesting for you guys is to look at an example which is based on this, all right? So example 1, wait a minute. Example 1, if we look at f of z, 1 over z, right? This is holomorphic on C minus, right? Well, it's holomorphic on C. It's actually holomorphic on Cx, right? But we have, as you may recall, d dz of the principal logarithm of z equals to 1 over z for z in the slit complex plane where we're removing the negative real axis, right? We've talked about this a number of times. So my claim is that you can actually construct the logarithm by kind of going backwards, right? Like, so check this out. We could give an alternate definition of log. Alternate definition, log z equals to the integral from 1 to z of the, I can't do it. I'm going to try. d zeta over zeta. All right, fine, I give up. dw over w. There we go. I can't use z because it has a fixed arbitrary meaning other than the integration variable, right? So I need another letter. So when you guys took Calculus 1, did you ever talk about the way we define log? No? Okay. All right, so because this is an alternate definition that can be given for the real logarithm. Like, if you look at Stewart or most calculus books, there will at least be homework problems or something where log of x can be defined to be the integral from 1 to x of dt over t. Like, you can take that as a definition for the real logarithm. I should say natural log in this context. Sorry, guys. For the natural log, you can define natural log like that, and you can actually prove its properties following from properties of integration. Some people prefer this method to introduce, and then you introduce the exponential as the inverse function to the logarithm. So in some sense, it's more rigorous. In another sense, it makes the introduction of the exponential sort of like really, really late in the course if you follow the logic to its bitter end. So I'm not a fan of this approach, but some people think it's like really, really cool. But anyway, this is the complex analog of that, is we could actually define the principal logarithm by this integral. Let me actually calculate one, yeah? So I'm just going to calculate in a particular instance I'm going to look at, let's see here. A second here. So I'm going to 1 to z naught in c minus, in particular see the union of the path from 1 to the absolute value of z. Okay, I got it. So let's say 1 is here, all right? And for the sake of illustration, here's the... So I'm going to assume that we're going to z naught like over here, all right? And so like the magnitude of z naught's larger than 1. So what I do is I go from 1 over here to the absolute value of z naught. That's a point on the real line, right? So I take that curve, and then I follow a circular arc like that over to here, all right, ending there. So that's the path I follow to calculate the log. Now, I suppose I should mention that we know that the integral of a holomorphic function is path independent. So I don't know if I proved that or not. Lost track of what I proved and what I haven't proven here, guys. A second here. I suppose that well, I guess in terms of logic, I could just I'm sorry, there's something missing for me at the moment, but let me stop. Let me not chase this rabbit here today. Okay, so how would I actually calculate this integral from 1 over here to z? So this is the log of z naught. All right, thinking of it in that context. So if I can get to it. So I'm calling this C1, I'm calling this C2, all right? And so the integral, and the whole thing is C. So the integral over C of dw over w, integral from over C1, dw over w, plus the integral over C2 of dw over w. All right, so particularly for C1, what's the formula? How do we parameterize C1? What do we have here? Here we just have z equals to t, right? For 1 less than or equal to t less than or equal to the absolute value of z naught, yeah? The modulus of z naught. So this first integral is just straight up integral from 1 to the modulus of z naught of dt over t, because dz is dt here. And okay, so how about the other piece? Here we can for C2 we can put z equals to the modulus of z naught e to the it, right, where 0 is less than t is less than, let's say, theta naught, where theta naught is the argument of z naught. Right? So I have integral from 0 to theta naught of, now this time dz is what? Absolute value of z naught I e to the it, right? Dt, yeah. So if we look at dz over z, what do we get? My bad. Well, I guess I should be saying w. Fine, I'll change it. W. dw. And this was also supposed to be w. My bad. All right, fixed. Sorry about that. Okay, so we have dw over w here. The e to the it's be canceling, and I think we just have I dt. Yeah. So what do you get? You get the natural log of the modulus of z naught minus the natural log of 1 plus I theta naught. In other words, you get the natural log of the modulus of z naught plus I arg of z naught. In other words, you get the function previously known as log z. But now we've obtained it from an integral. So this is another reason that the log has to be defined as it is. All right? If you look at my example 7.28, I show how to define logs of alpha by an integral. But it's a little bit sneaky, and I'm not going to talk about it in class. Last time we talked about Cauchy's theorem. And I guess I should just, since we did that last time first, I should just use that to logically, because I'm assuming path independence in this proof, right? First of all, Cauchy's theorem did not require this proof, right? We proved Cauchy's theorem from the complexified Green's theorem, right? So the Cauchy's theorem did not rest on this. It being before Cauchy's theorem is just an artifact of the history of how my notes were created, right? It's not a logical sequencing. My notes should be fixed in some sense, right? So my point to you is that we have Cauchy's theorem already, and Cauchy's theorem said what? It said that the integral around the boundary of a domain, of a holomorphic function on that domain, is 0, right? But I would remind you that we learned something in Calculus 3, right? We learned something in Calculus 3 about the relation between the path integral. Like there's a trichotomy, right? Like the following are equivalent, you know? I've done it all wrong. That's not good. The following are equivalent. So if we had if we have a complex function, right? I could put these three things. Number one, I think all of these are for f of z holomorphic on D. I think that's the context here. So let me just assume that at the start. All right, and D is a domain. D is a domain here. So so let's see here. The integral around a loop. Oh, rats. Sorry, I'm trying to reformat my notes a bit here. The integral of f of z dz is equal to the integral along C2 of f of z dz for coterminal paths C1 and C2, which are, inside D. That's the one thing we could say. Number two, we could say that the integral around a loop of f of z dz is equal to 0 for any loop in D. And yeah, I guess that's all I really want here. So I'm sort of bouncing off corollary 7.2.10, but I'm not faithfully following it. The corollary has a little bit more to say that I don't need to say here at the moment. But I would point out that number 3 would be that we have path independence of the integral of like f of z dz for C. Oh, well, I'm sorry. That's what I have up here. I'm an idiot. Let me erase that. Oh, good grief.
Yeah, I think that's one about like,
Sad.
loops contained in
Come on. Sorry. What's that?
I think it's one about like loops contained in other loops.
Right. Yeah, I have what I usually call the deformation theorem. So, all right. So all I want to say is that what I was worried about a second ago, I don't need to be worried about, because we already have a proof of 2 by Cauchy's theorem. Right? Because if you think about, if D looks like this, right? Whatever it looks like, I don't know. If I take a loop, right? If I take a loop like this in D, then I can argue that the integral around the loop for a holomorphic function is 0 by Cauchy's theorem. And then by the usual calculus 3 argument, I have independence of path. See, because, just to be more logical, pick 2 points, beep, bop, PQ, right? Then you can form a path like here, C1, a path like here, C2, right? Between those 2 paths, you can form a loop, right? So if I know the integral around the loop is 0, I can also look at the loop as what? Like C1 union with, so I should try to go counterclockwise. So C2 union with minus C1, right? And so if I do the integral along C2 union minus C1 of f of z dz, if that's equal to the integral of C2 of f of z dz minus the integral over C1 of f of z dz, right? But that's equal to 0 by Cauchy's theorem we proved last time, which proves that we have path independence. We have path independence for the complex integral of a holomorphic function. Provided what? There's strings attached here. Provided that, well, the paths have to be coterminal, I guess, is part of it. And this is a somewhat simplistic argument because you might consider the case that there's a hole in the middle. Oh, but it doesn't matter, right? Because if there's a hole in the middle, we still have Cauchy's theorem for holes. Like the domain doesn't have to be without holes. Cauchy's theorem is still true for a domain with holes. Yeah? You don't know? We stated Green's theorem last time. We talked about the outer domain is the outer boundary is counterclockwise oriented, and the inner boundaries have to be clockwise oriented. That whole business. Right, so we allowed for holes. And so if there was a hole, you can still form a loop around the hole. The more insidious thing to think about is what if your paths look like, what if the paths you're trying to prove path independence look like this? then you'd need to apply Cauchy's theorem on each little loop. Well, I think you could still apply Cauchy's theorem on the region which is bounded between the two curves, logically speaking. But to be totally fussy, maybe there's some analysis I'm skipping over here, truth be told. All right.
What we need is topological connectedness, right?
we would need a longer attention span to get through this proof is what we'd need. But yeah. But, well, I don't know, I would have to study properties of paths more carefully than we have in here to address that kind of issue. Okay, anyway. Part 3, though, is actually important. Part 3 is what I usually call the deformation theorem. So let me state this separately. Deformation theorem. If C1 and C2 bound, well, are the, let's say, are the boundary curves of an annulus, let's say. It doesn't, I don't want to say annulus. It could be of a domain. I don't want to insist that it's a circle. You know, I mean, when I say annulus here, I mean, let me just draw a picture to kind of give you the idea. So C1 might look like this, all right? And C2 might look like that. All right, so both oriented clockwise or counterclockwise. Like the orientations have to be matching, right? Assuming that. And if f of z is holomorphic on D, and by D I'm talking about the region that is bounded by these curves. So I said annulus, I mean, you know, and technically the domain wouldn't include the curves because it's got to be fuzzy. And I think to be more fussy, I actually need what? I need that the, come on, you got it in you. There we go. I need that the function holomorphically extends a little bit past the curves to use the theorems that we want to use. Remember, that was the terms and condition of Cauchy's theorem. We needed like the holomorphicity to extend a little bit past the boundary of the domain. If all of this is true, then the integral along C1 of f of z dz is equal to the integral along C2 of f of z dz. How would we prove this? I don't think I have proofs in the notes either because I've relegated these to homeworks various years. So, you know, because it's really calculus 3 in some sense, the argument. But here I would say it's not. This is just Cauchy's theorem. So like, here's the deal. The boundary of D, in my current picture, what's the boundary of D? Remember, I need clockwise inside loops. I need counterclockwise outside loops. What do I have right now? Counterclockwise outside loop, that's good. Counterclockwise inside loops, oops, that one's wrongly oriented. So the boundary of D is C1 union with minus C2, right? And Cauchy's theorem tells us that the integral over the boundary of D of f of z dz is equal to 0. So that implies that the integral over C1 union minus C2 of f dz is equal to 0, which implies the integral, I'm tired of writing, of C1 of f dz is equal to the integral over C2 of f dz. All right, so there you go. I could write a few more steps, but I'm out of whiteboard. Yeah.
deformation theorem. They both have to be oriented either clockwise or counterclockwise. One can't be oriented
Right.
clockwise.
They both have to have the same orientation, otherwise you'd have to put in some minuses.
But
You can always take a clockwise and turn it to counterclockwise by just putting a minus outside the integral, you know? So we've got that. But so let me show you an application of this theorem, because it's, you know, there's lots of applications of it. Example 2, right? What if I had the integral of you know, dz over z minus z naught, let's say, over c. And I'll draw a picture of what's going on here. Maybe here's z naught. All right. And the curve I have in mind is this. So what's the answer?
By I f of z naught?
There's no f here.
Oh, by I f of z naught, where f is what?
Which otherwise known as
2 pi I.
2 pi I, correct. Let me show you why that is. So what we do is the integral over, say, the circle of radius epsilon centered at z naught, right? Where epsilon is sufficiently small so that, like, it looks like this. So if we look at, you know, if we look at f of z equal to 1 over z minus z naught, for instance, that is what? Oh, you were using Cauchy's integral formula. Very good. But I was being less adventurous. Forget that you know Cauchy's integral formula for a moment. Imagine a simpler time when all you had to work with was Cauchy's integral theorem. Excuse me, Cauchy's theorem. The names here. Cauchy's theorem. The one that says the integral of a holomorphic function 0. That's all we got. Well, actually, we got the deformation theorem. So the point is, since the function f of z is holomorphic between the blue and the red, I know that the integral around the red loop is equal to the integral around the blue loop. But the thing is, we did this like day one. We did this day one. One of the first integrals we did was the integral over dz over z minus z naught of a circle of radius epsilon. And we proved that this is in fact equal to 2 pi I. So that's something we already knew. Previous example. But very good. Example 3, another way to do it, just like you said, is to look at it dz over z minus z naught. And you're like, well, that's really just the integral of f of z dz, different f this time, over z minus z naught, which is equal to 2 pi I. Let me put a g here just to be different. 2 pi I g of z naught. Right? Where g of z is what? 1. So this is 2 pi I. Now this one here, we didn't use the deformation theorem. This right here is Cauchy's integral theorem. Very good. That is another legitimate way to do this integral. All right? Nice. Very nice. All right. So after you guys finish the homework, which was originally due today, but now is due Tuesday, you should pretty well understand Cauchy's integral theorem and Cauchy's generalized integral theorem, the definition of the complex integral. All of these things should make sense and hopefully be more clear to you, right? I have as Exhibit A the student who finished the homework. I mean, I'm just saying, like, why does he know that Cauchy's integral theorem solves the problem? Is because he's used Cauchy integral's theorem to solve problems. It's not rocket science, right? If you do the homework, it will give you an unfair advantage over the other students. It's true. Did I ever? I think I've told you guys this story before, but there was that year of physics which complained that some of Dr. Skambordis' physics students were solving problems that he had not assigned, and it was giving them an unfair advantage. I still want this comment to be like not a joke, but a serious comment, because it comes from such an absurd place. But there were students working problems at the end of the chapter that were not assigned. It was giving them an unfair advantage. Okay, come on. That complaint had to be made by the students who were doing the extra problems at the end of the chapter, right? Most likely, truth be told. I mean, it's this, and of course surveys. Who knows? I like it. All right, so we're going to talk about Liouville's theorem. Let's get to it. And so Liouville's theorem rests on the generalized Cauchy's integral formula, which I'll write down again here. The mth derivative at z naught is equal to m factorial divided by 2 pi I, and the integral over modulus of z minus z naught. So this is actually a particular instance less than or equal to. No, just equal to, you dummy. Me, not you. That's supposed to be equals rho f of z dz over z minus z naught to the m plus 1 power. All right, so here we're assuming that f of z is holomorphic on a closed set D. So I think the context here is you got some D on which f is holomorphic, and I believe that this is a radius rho disk centered at z naught that we're writing this formula for. All right, so what then? So we can actually calculate this a little bit, right? This is what, m factorial over 2 pi I. We can integrate from 0 to 2 pi, right? F of rho, oh my bad, f of z naught plus rho e to the I theta divided by rho e to the I theta to the m plus 1. And let's see here. Just to be clear, I'm putting z equals to z naught plus rho e to the I theta as a parameterization of the circle. This is assumed to be, sometimes you see the symbol like this to indicate the orientation. Now dz would be what? I rho e to the I theta d theta, I think here. Let me check my notes, make sure I've got everything. So we can simplify that. What do we get? The i's be canceling. I think I get m factorial divided by 2 pi rho to the power m. Integral from 0 to 2 pi what? Oh, yeah, da, da, da. So f of z naught plus rho e to the I theta. I should just work it out rather than looking at the notes. It should be just as much work. So this is e to the I theta to the m plus 1. But then we have plus 1 up here, so we just get e to the minus I m theta, I believe, d theta. All right? Okay, so then say if f of z is less than or equal to m for z modulus of z minus z naught equals to rho, then, all right, then we can say that the modulus of f, the mth derivative at z naught, is less than or equal to, let's see here, we got m factorial divided by 2 pi rho to the power m. Let me just put equals for a second before I get to the less than or equal to. Absolute value modulus of this integral, right? So I just took the modulus, right? Now, the thing is, if I know that the modulus of the function is bounded above by m, then I can write this. This is less than or equal to little m factorial divided by 2 pi rho to the m, the integral from 0 to 2 pi of the modulus of f of z plus rho. Now this, right now I'm just using a property of the integral, all right? And I'm going to write some simplifications here in just a second. So you guys help me out here. This is what? What is the modulus of an imaginary exponential? Right, number 1, we got that. That's 1. And this, by assumption, is what? Less than or equal to what? M, right? Because notice that z, that's supposed to be z naught, my bad. Z naught plus rho e to the I theta is a point on that circle, okay? So that's by assumption less than or equal to m. So what happens when you do the integral? You just get m factorial over 2 pi rho to the m times m times 2 pi, right? Which gives us m factorial big M divided by rho to the power m. And so what we just derived, this is called Cauchy's estimate. He's got a theorem. He's got a how many theorems? Now we don't want to call it Cauchy's theorem. Then we're going to call it Cauchy's estimate this time. Doesn't he have enough? Can't he leave anything for anybody else? I mean, come on, Cauchy. I tell you, look at this. It's like there's no one else. So this is less than or equal to m factorial big M divided by rho to the m. In the context that we're talking about, right, which is that f is holomorphic and that m is a bound for the modulus of the function on the circle of radius rho, right? So now this brings us to Liouville's theorem, which I will state next. So is the fundamental theorem of algebra in the homework you just did?
No.
Nah, I guess that's the next one. I should always make students do the homework before it's due. This is very handy.
Shane.
Because I thought it was good.
It's texted in the group chat.
That's on campus.
No, the group chat. Yeah, really?
All right, so Lieville's theorem. It says the following. Suppose,
No, he doesn't tell me.
oh, he's got homework. F of z
I have 20 feet.
is holomorphic on the complex plane. Well, I have with continuous derivative on C, but we already know that's true. If modulus, I think at this point in the notes, I didn't have Gorsaw's theorem yet, but you know, since it's out of time, since we're studying this outside of its usual temporal sequencing, we don't have to put the with continuous derivative because we know it has a continuous derivative because it's holomorphic on C. If the f of z is less than or equal to m for all z in C, then f of z is constant. All right. So, proof. We know f of z and f prime of z, etc., are continuous on C by Gorsa. So we don't need to assume continuity of the derivative here. All right. So consider the disk of radius r centered at z naught. All right. Z naught, disk of radius r. Okay. What can we do? What does Cauchy's estimate tell us? In the m equals what case? Let's Cauchy's estimate with which one do we want to do? M equals 1 or m equals 0? I guess m equals 1. M equals 1. What does Cauchy's estimate for m equals 1 say? It says that the modulus of f prime of z naught, right, is less than or equal to what? 1 factorial m, right? So m is, we're assuming that. So if it's true for all, all complex numbers, it's certainly true for the complex numbers that are on this circle, right? So we have m divided by what? Divided by, what's the, well, the row here is r, right? So why does this prove that the function's constant? Can you guys complete the thought for me? No proof by Shane. Shane's not taking your test.
Oh, I know.
what if we thought about R? How big is R?
Oh, it could be anything.
It can be anything, right?
You can make it small.
So you can make R as big as you want. So what does that say about f prime of z naught?
It's gotta be 0.
It has to be 0, right? Because this can be made arbitrarily small. Very good. So as R goes to infinity, we find the limit as R goes to infinity of the absolute value of f prime of z naught is equal to the limit as R goes to infinity of m over R by Cauchy's, this is using Cauchy's estimate, of course, and that's 0. So therefore, the modulus of f prime of z naught is equal to 0. But what does that then say? That says that f prime of z naught is equal to 0, right? But which z naught did this argument hold for? Z naught was completely arbitrary, right? So thus, f prime of z is equal to 0 for all z in the complexes, right? And recall we had a theorem previously that if the derivative is identically 0 on a connected domain, then the function's constant. That's it. It turns out you can use this to prove the fundamental theorem of algebra, that every complex polynomial has at least one complex 0. Once you know that, then you can use the factor theorem to prove that it factors into a product of complex factors, linear complex factors, possibly repeated. But to crack the egg, you just need to show that an arbitrary nth order polynomial has at least one complex 0. If you can prove that, then the version of the fundamental theorem of algebra I always use follows easily from the factor theorem. So I think that's probably in your next homework, though, so I'm not going to get into it here. All right. Or maybe I saved it for your test. I don't know. We'll find out. What, too soon? All right, so with that, I'm going to go and show you guys some stuff from Chapter 4 in Saff and Snyder. Well, I'm just going to read a couple of results from 4.6. 4.6, Theorem 22 actually says every non-constant polynomial with complex coefficients has at least one 0. So the proof of the thing I was just talking about is actually written on page 216 of the book. You can read it there. So if I assign that homework problem, the solution's already here, if you want to think through it. Then lemma 1 on page 217 says, suppose that f is analytic in a disk centered at z0, then the maximum value of the modulus of f of z is the modulus of f of z0. Excuse me, that's the condition. Suppose f of z is analytic on a disk centered at z0, and that the maximum value of the modulus over the disk is the modulus of the function at the center of the disk, z0, then the modulus is constant in the disk. Theorem 23, known as the maximum modulus principle, says the following. It says if f of z is analytic in a domain D, then the modulus of f of z achieves its maximum value at a point z0 in D. I keep messing this up. If f of z is analytic in a domain D and the modulus achieves its maximum at a point z0 in D, then f is constant in D. So if the modulus is maximized at some point in the interior of the domain, domains are their own interior because they're open, then the function has to be constant. So if you want a non-constant holomorphic function, it must be that the modulus attains a maximum on the boundary of D, not in its interior. Anyway, so that's some of the results from section 4.6. Yeah.
What about in its exterior, or is that just not possible?
Well, I mean, we're just talking, I mean, you could think about that, but I'm just talking about, those theorems are about the maximum of the modulus of the function with respect to a domain. So we're not talking about what happens outside the domain. All right. So let me write down something, and I'm going to do a calculation here if we have time. I hope we have time. There's a neat calculation at the end of section 4.7. Does this thing not work? Yeah, okay, we're fine. What it is? No?
What?
Is there, it's all good?
Yeah?
Okay, okay. I heard, I don't know what the,
Jordan, he was jabbing back there.
it was Jordan.
Yeah. he was
That's
jabbing back
interesting,
there.
interesting. Let's see here, so. So see, here's some results from section 4.7 of Saff and Snyder. So theorem 25 is something I think I was supposed to prove last part of this course, but I think I forgot to. Let phi, I almost put this on your test, be a function harmonic on a simply connected domain if you want. Then there exists f in the holomorphic on D. I'm going to call this domain D. All right. Then there exists f holomorphic on D such that phi is equal to the real part of f on D. In other words, what this theorem says is that our program to find a harmonic conjugate, it's guaranteed to succeed. We didn't really talk about this. We just worked problems. We didn't ever stop and ask the question, wait a minute, does there exist a harmonic function where this doesn't work? Right? We just worked problems and they all worked out. So, but that doesn't prove this theorem, does it? So, so I guess we can look at the proof. So the proof he gives a little bit, he starts with a little bit of a motivating thing. He says, if f was equal to phi plus I psi, all right, then f prime should be equal to, partial phi, partial x. What? Well, let me just, duh.